Our YouTube channel, Mr. Grant Justice. Give him a hand. All right, check this. All right, let's go ahead and get started. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I am Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure to be your host. When you came in early, you might have gotten a picture of the star cluster Westerlund 2. If you came in a little bit later, we ran out of Westerlund 2, and now we have the star-forming nebula N90 available. If you get these, the N90s are still available. If you want the Westerlund 2, well, you might have to trade with somebody, okay? So do your best horse trading, and you can get your wonderful pictures. If you'd like to know more about them, of course, turn over on the back, and we have a short essay telling you about them. Our topic tonight, a fun one, mapping the United Federation of Planets, an astronomer's guide to the galaxy. And of course, everyone recognizes that the United Federation of Planets is a reference to Star Trek. And Mia has told me that, yes, she will tell you where the Klingons are. All right? Next month, Susanna Deustua will be talking about the plumes of Europa, ice, water, life. Find out next month, April 3rd. In May, one of the talks we've been trying to get for a while, recently won a Nobel Prize, gravitational wave astronomy, a new method for examining the universe that we can now finally detect gravitational waves. We've only been trying for about 40 or 50 years to see what we can do. We can finally detect them, and Andy Fruchter is our local expert who will tell you about that. On June, Will Fisher will speak on one of my favorite nebula in the entire universe, the Orion Nebula. It is the nearest large star-forming region. It is our template for understanding star formation in the universe, and the guys here know so much about it. He'll give you all sorts of cool detail on how stars are born. Actually, not only stars, but also planetary systems. All right, that will be in June. The details are on our website. In your favorite search engine, type in Hubble Public Lectures, and you should find this webpage where we have the list of the upcoming talks. Oh, by the way, I see Mia Bovill is on a grab from 2016. So she has spoken here before. That was just a screen grab I did here. We also have the online, the live, the YouTube and STSCI webcasting, as well as the archives. The YouTube goes back to 2014. The webcast goes all the way back to 2005. That's a lot of astronomy topics. I dare you to binge watch that in one weekend. I don't think you can do it. If you would like to be informed, we have our sign up for our email list, both subscribe and unsubscribe. If you would like the announcements, we say, as I just told you, sign up at the website. Or if you can't possibly do that, give me your email, okay? I'll write it down on a piece of paper, hand it to me, and I'll make sure you get on the list. If you have comments or questions, we have an email, publiclecture@stsci.edu. You can send email to that, and we'll get to the answer. All right. Social media, Hubble, Web, and STSCI have a variety of Facebook, Twitter, YouTube, and Instagram. I myself do a little bit of Facebook, Google+, and Twitter, and some occasionally write some blog posts if you want to hear more from me. Unfortunately, if you looked up, you could not see any stars tonight. It's cloudy. It's going to rain and possibly even snow a little bit tonight. So, yeah, no Maryland Space Grant Observatory tonight. But if you go to md.spacegrant.org, you can find this page, and they have open houses every Friday. You want to check this page for the observatory status right over here on the right-hand side, and they'll tell you whether or not they're going to be open on various Fridays. Okay? And now, news from the universe for March 2018. And since our speaker has chosen a sort of Star Trek theme to her talk, I decided I would add a little bit of Star Trek flavor to my news summary. So our first topic is, Warp factor 500 million. When I'm talking about warp, I'm actually not talking about the Star Trek warp. I'm talking about warped images. And this is Baltimore's Inner Harbor with a Saturn mass black hole passing over the Inner Harbor. And you can see that the images of the background buildings are warped by the passage of that black hole. Because due to general relativity, mass bends space, which changes the direction of light. So as you look past a black hole, the light goes around in different directions, and it warps the images of the background objects. It doesn't actually warp the background objects, but it warps those images. Now, that cannot just happen here in Baltimore. Actually, it's never happened here in Baltimore. That's just an example. But it can actually happen out in the universe in clusters of galaxies. These clusters of galaxies have so much matter, mostly dark matter, in them that they are massive enough to bend the space around them, which actually changes the direction of the light passing through them. We call this gravitational lensing. Gravity changes the direction of the light, and it acts like a lens in space. So if you've got this lens in space, and you've got a telescope lens, this actually acts as an extra lens to magnify and amplify the light of more distant objects. Using these gravitational lenses, we can see some of the most distant galaxies out there. And so in this cluster called MAX J0647 plus 7015, they don't have any great names, they're usually just phone numbers like that, we actually found a really, really distant galaxy, and there are actually 3 images of it. The light from this extremely distant galaxy passes 3 ways through this cluster, and appear here, here, and here. And you can see it's beautiful. It's a red dot. Okay, but that's because it's a galaxy about 13 billion light years away, one of the most distant we've ever seen. And when we do this, that's what we usually get. We get red dots because they're very small galaxies, they're very distant, and therefore they're seen in the early part of the universe. Okay? If it's 13 billion light years away, you're seeing that galaxy as it was 13 billion years ago. Okay? That's only 800 million years after the Big Bang. That's a really baby galaxy, okay? But this was something that was released a few years ago. We have a new cluster that we looked at. This one has the phone number SPT-CL J0615-5746. And in this one, we do not have a red dot. In this one, we actually have a red streak. We have a red smudge. So this may not look like much to you. Okay, so you got it's a blur of red instead of a dot of red. But actually, by getting a red streak, the gravitational lensing spreads it out, turns it into a streak. You can actually examine some of the internal characteristics. You can estimate it. This was found using the Hubble Space Telescope and the Spitzer Space Telescope using a program called RELIX, when they searched 41 large clusters of galaxies looking specifically for these most distant objects. And this object, they can tell, is only about 2,500 light years across. Now, our galaxy is 100,000 light years across, so this is tiny compared to our galaxy. Our galaxy also has about 200 billion stars, and the estimate on this is it's about less than 3 billion stars, okay? So it's very small. It's a dwarf galaxy. It's only half the size of what we call the Small Magellanic Cloud, which is a dwarf galaxy that's orbiting around our Milky Way. But you wouldn't expect it to be a large galaxy because this galaxy is estimated to be seen 13.3 billion light years away, which makes we see it only 500 million years after the Big Bang. And that's a crucial idea, that galaxies of on order a few billion stars can form within the first 500 million years. How long after the Big Bang does it take for stars and galaxies to form? That's one of the great questions in cosmology that we're pursuing. This gives us evidence that at least you can get a few billion stars together in one sort of clump 500 million years later. Now, Hubble can't see the most distant galaxies because they're redshifted into the infrared. So this is sort of a precursor for what we will see with the James Webb Space Telescope that's currently slated to launch in spring of 2019. So a little over a year from now, the James Webb Space Telescope will launch, and after it becomes operational, we'll get more and more images like this, and you can expect me to give you more and more stories about looking at the first billion years of galaxy formation and having much greater statistics and getting an understanding of how galaxies initially formed in the universe. So this is a great, cool precursor. And I named it warp factor 5 million because using the warp created by this galaxy cluster, we're able to see back to 500 million years after the Big Bang. Our second story. Lack of J-class atmospheres raises hopes of M-class planets. All right, so if you know your Star Trek, okay, you know that almost everything they visited was, Captain, it's an M-class planet, which means an Earth-like planet, okay? I actually looked up on Wikipedia today. They have 23 different classes of planets defined in Star Trek. It kind of blew my mind, the specificity they had of these 23 different classes of planets. And it found out that the J class is the Jupiter class, Jupiter, Saturn, Uranus, and Neptune gas giants. Although they aren't the only class of gas giants. There's several different classes of gas giants. I think the largest is the T class or something like that. I'm not a Trekkie, so I don't know all this stuff. But I'm using that to talk about the planets in the system TRAPPIST-1. Now, this is an artistic presentation of the TRAPPIST-1 system. We talked about this before, in which there are 7 Earth-sized planets around a red dwarf star. And this artistic presentation is supposed to show that, okay, here we have the red dwarf star, and here we have steam to indicate it's hot. Water would be boiling away. Here we have water in its liquid form in the middle, and out here we have water in ice form where it's cold, okay? And several of these planets in the TRAPPIST-1 system are in the region where liquid water would be liquid, and that's what we call the habitable zone, all right? If you want a more didactic presentation of it, here is the TRAPPIST-1 system with the red dwarf star here, and the 7 planets, B, C, D, E, F, G, H. You've heard of Snow White and the 7 dwarfs. This is red dwarf and the 7 Earth-sized planets in the TRAPPIST-1 system. Now, this is artistic interpretation, okay? Do we know what these planets look like? No, not at all. We don't actually see the planets. What we see is the planets pass in front of the star and block a little bit of the light, so the light for that star drops and rises back up as the planet passes in front. We call this the transit method of finding extrasolar planets. And we found 7 of these around this star. So we don't actually see the planet, but we could see its atmosphere, because when a planet passes in front of a star, some of the light of the star will go through that planet's atmosphere. And the chemical elements in that planet's atmosphere will absorb some of the star's light. So if you take a spectrum of the star, and then you take another spectrum with the planet in front of the star, subtract the two, you get the spectrum of the planet's atmosphere. How cool is that? We can actually start to see the atmospheres of planets around other stars. So we wanted to tell, do these Earth-sized planets have Earth-like atmospheres? All right? And so what we can tell here is if it has a big extended atmosphere, we'll see a lot of absorption. Okay? This big extended atmosphere we'd expect to be hydrogen, puffed up, a primordial type atmosphere. Okay? However, if it has a thin atmosphere, sort of like Venus, Earth, and Mars have today. It's not primordial, it's processed, it has a good amount of heavier elements in it, well, then it would have a thinner atmosphere, and we'd see almost no absorption, okay? So if it has a big atmosphere, we're going to see absorption. If it has a small atmosphere, we're not going to see absorption. All right, here is the actual data, okay, presented in an artistic fashion. The purple is what we would expect if it had this large primordial atmosphere. The yellow is the actual data. And you can see that the actual data in the yellow is consistent with basically a flat line, not the big up and down that we see in the primordial atmosphere. So for these 4 planets, 3 of them, D, F, and E, all in the habitable zone, we do not see a large primordial atmosphere. G, we're not quite sure of, okay? Then we need a little bit more. We can't say with absolute certainty that G doesn't have a big atmosphere. Most likely it doesn't, but you know, we have certain measures of this, and this one's not good enough to say for sure. So, this lack of this J-class atmosphere indicates that it could have an M-class atmosphere, but does it say it absolutely has an M-class atmosphere? No. It just says it doesn't have a large extended atmosphere, which adds to the hope that these could actually be more Earth-like. They're not Neptune-like, okay? Sometimes we think of these Earth-sized objects. They could be super Earths. They could be mini Neptunes. These are not mini Neptunes, okay? They don't have extended atmospheres like this. So one check mark, yes, in terms of moving forward, in terms of trying to find Earth-like planets. We know they're Earth-sized. Now we're continuing to try and find out if they're Earth-like. And this is a good sign moving forward in that direction. Again, we will find more out when we have the infrared observations of the James Webb Space Telescope, because extrasolar planets actually shine in the infrared. They're brighter in the infrared, especially relative to their host stars. So, again, pointing to the future, we're going to have a lot more of these type of stories as well when the infrared space telescope, the Webb, is up there in next year and the year after. Okay? All right, and so that is our news from the universe. Our featured speaker tonight is Mia Bovill, who has, this is like your 3rd time talking here, right? She's wonderful because she comes and she volunteers for me every year, okay? There are a number of speakers who have to twist their arms to volunteer once every 5 or 10 years, okay? But Mia has come in, and last time you talked on the Harvard computers, right? That's what you called them, okay? And tonight she is going to talk to you about the science of observing the galaxy with a wonderful Star Trek flair. So, ladies and gentlemen, Ms. Mia Bovill. Dr. Mia. I will call you Doctor. Whoops.
All right.
I missed you. There we go.
All right. So first off, I'd like to apologize to every single person in this room in a red shirt. All right. Now, like a good scientist, you cite your sources. So for the science chunk of this talk, I used Galactic Astronomy. This is one of the Bibles of our galaxies course. What I'm going to cover, the mapping of the Milky Way, is a month in a graduate level galaxies course. And I'm going to attempt to do this in 40 minutes. So I might leave a few things out. And for the rest of it, so this is the Star Trek Atlas. I actually had to order this from San Luis Obispo, California, because apparently it's no longer in print. But for the mapping of specific worlds to specific actual real stars, which I'll get into towards the end of the talk, this is what I used. If anybody is a bigger Trekkie than me and wants to take issue with exactly what star I plotted, just look at this first. And I'd like to just point out that I do have a towel in my backpack. All right, so just to get this out of the way, Star Trek is wonderful. It does a lot of things really, really well. Science is not one of them. So this is a list of the things that Star Trek, roughly speaking, gets right. We live in the Milky Way galaxy. The Milky Way galaxy is about 100,000 light years across, though how much of that is them getting it right and how much of that was dumb luck, I'm not actually certain. There are nebula in the Milky Way. They won't eat your ship. They won't corrode your ship. And they are significantly bigger than your ability to jot in and out at impulse. There are stars in the Milky Way. Many of those stars have planets. In fact, we have been finding a lot of them. This is as of December of 2017, and it probably needs to be updated. The Kepler, this is the full thing of the Kepler Space Telescope. So this is all the one-planet systems, 2, 3, 4, 5, 6. This is the TRAPPIST-1 system that Dr. Summers was talking about, our solar system, and the Kepler 90 system. So there are planets around stars. In fact, there are a lot more planets around stars than we thought there were. Some of these planets may be in the habitable zone of their star. And by habitable zone, I do not mean M-class with the Vulcans on them. I mean they are at the right distance from their star to have liquid water on their surface, which means you've got a chance at actually having life. Whether that life becomes intelligent and develops warp drive, well, that's a complete other set of questions. There are such things as neutron stars, pulsars, black holes, dark matter, and supernova explosions. The statistical chance that they used these correctly in any given Star Trek episode is about 10%. They do occasionally get this right, but more likely than not, they get it wrong. And no, you cannot punch your way through the event horizon of a black hole. But primarily, space is big. However big you think space is, it's bigger. However weird you think space is, it's weirder. So now that we've gotten that out of the way, before the Enterprise, you can tell the Enterprise or whichever particular starship you're on to go to, I don't know, insert technobabble here in this sector. First, you have to know where on Earth that sector, or in the galaxy, that sector actually is. And these are actually the only two good images I could find from Star Trek episodes of the various characters standing in front of a map. But before you can start to say, where did the Enterprise go, you first have to figure out where we are. And that starts with a very seemingly simple question. Where is the Earth located in our solar system? The planets, well, 5 of them are extremely bright. They're very easy to measure. In fact, we've been measuring them for thousands of years. But it's actually not so simple, because we have to go even further back in time, back to 270 BC and the golden age of Pericles' Athens. This is Aristarchus of Samos. And he went against the grain a little bit. He believed the sun was at the center of the solar system, that other stars were extremely far away, and that there were other stars like our sun. And that's why, as the Earth moved around the sun, we didn't see those stars move against the sky. However, he was only one voice. And at the same time, there were some pretty big voices saying that, no, the Earth's at the center. We're stationary, everything moves around us. And this was Aristotle here, and Ptolemy, as in the Ptolemaic system. He's the poor schmuck that gets this named for him. Now, you have the Earth here at the center, you have the moon going around, and you have the sun going around, all in perfect circles. However, the problem is that if you actually look at the movement of a planet on the sky, it'll kind of go this way a little bit, and then it'll kind of go this way again, and then it'll go back this way. And the part where it went backwards was retrograde motion. And if everything's just orbiting the Earth, happy as you please, you're not going to have retrograde motion. So they inserted what they called epicycles onto each of these orbits, depending on how much of the time the planet went backwards and how frequently it went backwards. And this worked. They could predict with the circular orbits around the Earth and epicycles, they could roughly predict the positions of the planets. Because that's your holy grail. That's what you want to do. You want to be able to predict where the planets are going to be. The problem is that as you move forward in time, the model kind of fell apart. The predictions with just one epicycle weren't working. Now, if that's getting further and further off the actual position of the planet, you would think, well, maybe we should go back to what that other guy was saying and try heliocentric. They just added more epicycles. There's a principle in science called Occam's razor. It's that the simplest solution is probably the best. So we're going to jump forward to 1609. This is about 30 years after Nicholas Copernicus once more resurrected the idea that, yes, the sun is at the center of the solar system. But like Eratosthenes and Aristotle and Ptolemy, he assumed the planets were on circular orbits, perfect circles. Enter these two gentlemen. This is Tycho Brahe. He was an incredibly fast talker. He somehow convinced the King of Denmark to give him a castle and build him the most state-of-the-art observatory in Europe. I really want to know how he did this because I've got grant proposals due. For 30 years, he puts together the most accurate set of measurements of the planets in existence. He's able to do, because he has these huge instruments, this is a sextant that allows him to measure very accurately the positions. He's still going by naked eye. He's not using a telescope. Galileo Galilei hasn't happened, well, he's alive, but he hasn't actually aimed a telescope at Jupiter yet. And after 30 years of developing all of this data, he passes that data off to Johannes Kepler. And that's a name that if you've been following all the planet formation, we named a planet-finding mission for him for a very good reason. Brahe tells him, look at Mars. Mars is the weird one. If you can solve Mars, you can solve all of it. And Kepler, keep in mind, there's no computers for the younger people in the room. There's no scientific calculators for the slightly older people in the room. And slide rules haven't been invented yet for the rest of the people in the room. This is what Kepler figures out, that the orbits of the planets are not circular. They're ellipses. Now, it just so happens for the orbit of the Earth, if I were to plot a circle on this slide and then plot the orbit of the Earth on top of it, you would not be able to tell the difference. It's extremely close to a circle. But for some planets, this is the inner solar system, like Mars, they're further off a circle. The further off a circle, the more elliptical or eccentric is the term we use the orbit is, the more clearly this comes through. So we have the Sun, Mercury, Venus, Earth, Mars. The asteroid belt, which we know is there, but they didn't. They knew about Jupiter, which is here, and Saturn. That's it. Uranus and Neptune will have to wait for telescopes to be discovered, and there is no way they know about Pluto, regardless of its status. And just as a reminder that we are already very much in space, all of the green things on here are space missions which are currently out there. That is the location of all of the space missions in our solar system as of this year. This is Pioneer 10, Pioneer 11, and Voyager 1 and Voyager, or I guess Voyager is what it ends up. 1 and 2 are going off in different directions for the edge of our solar system. So there's a reason we named a planet-finding mission for this guy. So we now know that Earth is the third planet orbiting a relatively boring G2 star. We're actually lucky it's boring. But how far away are those stars? So we know they must be pretty far, but how far are they actually? And now we need some audience participation without hitting the person next to you, or hit the person next to you if you don't like them. Hold your finger out in front of your face at arm's length. All right? If you can wink between one eye and the next, do that. Otherwise, use your hand. Does your finger move? Yes. All right. Now, stop using your finger and do the same thing with my arm. Now do this with my hand. Now, put your hand down and jump between, and does my hand move? A little. For the people in the front, a little. For the back? No. That is parallax. Every single time you walk down the street and don't run into something, you're using parallax. And that's the fact that your eyes are separated is actually allowing you to have depth perception. For those of you with glasses, and I mean the people like me whose eyes just don't work, if you've ever taken off your glasses, you'll promptly run into a wall. That's why. So when you take this, and instead of being our eyes and our heads, you actually talk about the Earth, you have the Earth has an orbit. It is 1 astronomical unit, about 93 million miles from our sun. And if you observe a star in January and observe that same star in July, so here's your star, and you look at it, if that star is close enough, it'll appear to shift, just like your finger did. This is parallax. The baseline that we have is 2 astronomical units. That's how wide it is. The wider the baseline, the larger the angle. The closer the object, the wider the angle. And the further away an object is, the smaller the amount of parallax you will see. And it turns out that there are not many formulas in astronomy that are this simple. This is the distance to the object, to a star. This is the parallax in arc seconds. So does everyone here have a sense of what a degree is on a circle? If you were to draw a circle, you have a sense of how much of that circle is a degree. Now, imagine that degree is the equivalent of an hour of time. An arc second is 1 second to that hour. It is 1/3600th of a degree. I could try to draw that on an arc on this, but you would see an infinitesimal line, if even that. This is an incredibly small measure, and it is at least 2 orders of magnitude smaller than what the person with the absolute best vision can see with their naked eye. Again, those of us with glasses need not apply. It turns out that if something has 1 arc second of parallax, or if this shift is measured as 1 arc second, it is 3.26 light years away. We call that a parsec. This is the primary unit astronomers use. It has nothing to do with the Kessel run, and it is not a unit of time. So I didn't say Star Trek was the only science fiction universe that messes the science up. I don't think they were looking things up in dictionaries. So they've known that this was going to happen. If the sun was at the center and the Earth is moving around it, you know the stars are going to have parallax. And they've been looking for this for about 2,000 years. It takes until 1838 for us to have the technology to measure parallax. And that is because to measure parallax, you have to measure 1/10 of an arc second. In 1989, a catalog of extremely bright and nearby stars was identified. This was called Hipparchus. It was one of the first attempts to do a large catalog of these stars and to get parallaxes for them. In 2013, the Gaia space mission was launched by the European Space Agency. Just as an aside, the process of mapping the Milky Way is very much an international endeavor. This is the Gaia spacecraft, well, an artist's rendition of the Gaia spacecraft. We're not out in space, and the Milky Way isn't that pretty. This is Hipparchus. So this is the amount of parallax the mission can measure in arc seconds. All of these points, so this is Tycho Brahe, actually like the Tycho Brahe, the guy that convinced the King of Denmark to build him an observatory. He also got his nose cut off in a duel. So this is about 1600. You have Hipparchus in ancient Greece that attempted this with 1,000 stars. And then you can actually see the technology improving. The blue line is how accurate your measurement has to be able to observe parallax around the nearest star to the sun, which also happens to be in the wrong hemisphere for Greece. It's Alpha Centauri. It's in the southern hemisphere. So you finally get down to the Hipparchus mission. This is 120,000 stars. A little later, there's a reason I'm explicitly mentioning this one. And then 2013 is the launch of Gaia. which is 1 billion stars. And Gaia is measuring parallax of 100,000th of an arc second. So if a degree is an hour, this is 100,000th of a second, is how accurate Gaia is. That kind of accuracy, the increase in accuracy, means increased distance to which we are able to measure parallax. And Gaia, for the brightest stars, is going to get all the way to the galactic center. So we have parallax. We can start to observe stars. Right now, we can go out to about 100 to 1,000 light years, depending on the star we're looking at. And that is step one. So determining distances, determining where something is on the sky, we've actually gotten pretty good at it. It's actually called astrometry. Something else Star Trek got right. Astrometry is the location of things on the sky. Figuring out the distance is a whole different game. And it is we call it the distance ladder. The first rung of that distance ladder is parallax, is using the shift of the stars. Second are things we call standard candles. And they're not actually these kind of candles. These are astronomical sources. So you have a source that is a standard candle. It can be a star. It can be a supernova, whatever it is. What's important is that you're able to get its absolute brightness, its luminosity, by a different means, from physics, from its period of its brightness oscillation, something. And then some distance away, you have the observer. I thought about doing a cute picture of the Enterprise, but they're not always on Earth. And the way that this works is actually relatively simple. You have the luminosity of the object, which you're able to figure out by some means. You have the apparent brightness that we measure on Earth. And the distance between that object and us is simply the luminosity over the apparent brightness. There's some physical constants and things in there, and the distance this is actually distance squared, but once again, this is very simple, very, very straightforward. In fact, this is the same 1/r² law that governs gravity. So we're going to jump forward to 1908, and work by Henrietta Swan Leavitt. She worked with, she was among 220 computers. And these actually were women that were doing computing. Again, these things called computers, apparently in 1950, they took up the size of a room, or so my father tells me. And Henrietta Leavitt was only one of them. The work that they did actually forms the backbone of our understanding of the stars. And just as a note, since it is Women's History Month, 140 of the names are known, 80 of them are not. We only have initials. Henrietta Leavitt she had an undergraduate degree in astronomy, and she was given the task of looking for variables. Not go look at these specific variables, just here's some glass plates. They were actually glass. You can see a crack here. These are actually glass plates. Some people in the room may remember film cameras. I think some of you may not. Instead of film, this actually was, you would take it on a silvered plate of glass. This is the SMC in a more modern image of the Small Magellanic Cloud. This is a period image of the Small Magellanic Cloud with her notations on it. These are her notations. And she noticed that there were a class of variables in the Small Magellanic Cloud that were very distinctive. They rose in brightness. They were stars that rose in brightness very quickly and then fell off, and then rose in brightness again and then fell off. They named them Cepheids for the prototype star for which they were identified. And since she had the SMC, she knew they're all at the same distance. They're basically all at the same distance, and the brighter Cepheids had longer periods. As of 2009, we actually call this the Leavitt law. This is the first standard candle. If you know the period of a Cepheid, you go up, you have its period, you go up, and you can read off its absolute brightness, its luminosity. If you have its luminosity, you have its measured apparent brightness, you have its distance. And Cepheids are bright. We can see these in external galaxies. They also are not that rare, and this is what you have to do to jump a rung of the distance ladder. It's not as simple as doing this. First off, you find a Cepheid that's close enough to also have a parallax measurement. Then you calculate the distance to that Cepheid using parallax and using the distance modulus, so using the relation between absolute luminosity, apparent brightness, and distance, you calculate the luminosity of that Cepheid. You then use that luminosity to calibrate the Leavitt law, to calibrate Henrietta Leavitt's relation, because you need to know where things sit on the luminosity axis. Does a Cepheid with a period of 2 days have a luminosity of 10 times the luminosity of our sun, or 100? That's a very large error that you're introducing in your distances. You then use your calibrated Leavitt law to get the luminosities of Cepheids for which you know their periods, Cepheids which are too far away for parallax. You then use the Cepheid luminosity and the apparent brightness, and you calculate the distance. Simple. Turns out their Cepheids are not the only standard candle. I'm focusing only on ones used to map the Milky Way. There's a whole long list of these. This is spectral class or color of a star from red to blue versus its absolute brightness. Our sun sits right here on the main sequence. All these stars are burning hydrogen, are fusing hydrogen to helium in their cores, and this is where stars will spend the majority of their life. And they're stable when they're on this. However, once they move off it, they become unstable. And they move through something called an instability strip, and these are where a lot of variable stars are. You can see this is the prototype for the Cepheids, the archetype for the Cepheids, and this is the archetype for another class called the Ara Lyrae. Like the Cepheids, they have a relation between their luminosity and their period. But unlike the Cepheids, they are older. So you can find these in evolved stellar systems, and that's going to be important in a minute. So we now know how far the stars are away, and that is somewhere between 4 light years and about 100,000 light years. I warned you space was big. Now, where is the solar system in our galaxy? So we're going to jump back to 1772 to William and Carolyn Herschel. They were brother and sister, astronomers living in England in the 18th century. I think something else was going on with England in 1772, but, just small kerfluffle with, some problematic colonies. And William Herschel, based on observations of stars, came up with a model of the Milky Way, which you can see here. He notices that when you look up, has anyone here seen the Milky Way in a dark night? All right, you see the arc of it, so there's a high density area of stars and fewer stars above and below. So he has that here. You can see that there's definitely a direction in which there are more stars. This is where the sun is. I just want a wild guess about whether or not this is right. No. Anytime we're at the center of the universe, you have a problem. It's actually called the Copernican principle. Never put the Earth at the center of the universe or in a corner. But to fully solve this problem, you had to wait 150 years. This is Howell Shapley. He was actually the second director of the Harvard Observatory. And he used Ara Lyrae variables, remember that second standard candle, and was able to get the distance to globular clusters. And unfortunately, the telescope's not working, but globulars are very dense, massive clusters of stars that orbit our Milky Way. And if these are things that are in the halo, in the outskirts of our galaxy, and you look at and you can measure the distribution, if the sun is at the center of the galaxy, then the globular clusters should be centered around us. If we're not at the center of the galaxy, the globular clusters shouldn't be centered around us. And he plotted the distribution of the globular clusters in physical space. So this is in kiloparsecs, so thousands of parsecs, or about 3,000 light years per unit, versus this is up and down in the plane. So this is the plane of our galaxy right here. And he found out that, lo and behold, the sun is not at the center of the galaxy. I mean, I'm sure this was shocking, but The sun is not at the center of a galaxy. In fact, the center point is in the direction of the constellation of Sagittarius. He believed it was about 14 kiloparsecs away. He was off by about a factor of 2. In astronomy, we call that an error bar. This is the diagram of our Milky Way edge-on. You have the disk of our galaxy and the bulge. For the record, the bulge is not that pretty. The sun is here about halfway out on the disk. The whole disk is 100,000 light years across, with the globular clusters orbiting the entire system. So we are not in the middle of things. We are in Loudoun County. Not on the complete edge of things, but relatively far out. So we know where we are, that we're out on the edge, that we're in the disk of our Milky Way, that the Earth is not at the center of our solar system, and that the stars are very, very far away. But what does our galaxy actually look like? This is an image, this is a composite image taken by the European Southern Observatory. So this is, a telescope cannot take this in one image. This is actually an all-sky image. It's beautiful, absolutely beautiful. The center of the galaxy is right here. But there's something in the way. So this is the disk, and there's all these dark spots. These are dust clouds. Now, this is not the kind of dust that you have to sweep off your floor. It's actually good that you have it. These dust tends to form in areas where there is a lot of star formation. We are actually sitting on a dust aggregate right now. In the early days of the planetary nebula, dust particles started to clump together. And then they become rocks, and then the rocks start banging into each other, and then they become asteroids, and the next thing you know, you have Earth. But they are a problem, because visible light, the light we see with our eyes, cannot penetrate that dust. The dust blocks it. So if you want to observe the center of the galaxy, if you want to observe really anywhere in the galaxy beyond our little region, you've got a problem. The good news is that there's more light than just visible light. This is the Eagle Nebula, the pillars of creation in the Eagle Nebula. For those of you that remember, this was on the front page of the Washington Post when the original image came out. This is invisible light, this beautiful multicolor image in visible light. This is the same shot in the infrared. So infrared light has a slightly longer wavelength that's slightly redder than visible light. It's how your cat knows where the food bowl is in the middle of the night. And if you've ever used night vision goggles, those are using infrared. It's also, we perceive it as heat. Our bodies are giving off infrared radiation in the form of heat. But what's incredible is these stars are here in this image. We didn't just ship them in special for the infrared exposure. It's just in the infrared light, you can look through the dust and the gas of the pillars to the stars behind them. And when you do that for the entire Milky Way, things look a little different. This is the Milky Way. This is a composite image in near infrared, in the near infrared part of the spectrum. You can now see the stellar disk of the Milky Way and the stellar bulge. The dust lanes that were blocking our view have faded completely into the background. And when we start looking towards the galactic center, which is about 8.5 kiloparsecs or 25,000 light years away, when we look in, we find that there is an extremely bright radio source called Sag A star, right at the supposed location of the center of our galaxy. And when we zoom in further, we see that the galactic center isn't just some stars moving around, it's actually a very complex region. And there's this incredibly bright source at the center. And when you zoom even further in, I hope this works, and you look, this is the center. These are stars. This is not a movie or an artist's conception, this is data. This is data taken over a period of about 10 years. For comparison, it will take the sun 250 million years to orbit the Milky Way. These stars are moving incredibly fast. It turns out that using Kepler's laws, using the laws Johannes Kepler determined for our solar system, you can take one of these orbits and figure out how much mass is in the middle there. It's not emitting any light, it's very compact, and it's 3 million times the mass of our sun. This is the supermassive black hole at the center of the Milky Way. So if you want to know where the center of the Milky Way is, that's it, right there. Here's the, and again, this is where I have to take what we do in a month in graduate galaxies and compress it. This is the optical, Milky Way disk and optical. This is the near-infrared image that I showed you before. When you look in the mid-infrared, further to longer wavelengths, you're now seeing the dust heating up, all those dust clouds heating up. That's what you're seeing here. When you start looking at molecular hydrogen, this is hydrogen that's bonded, so it's H2, it's 2 atoms of hydrogen bound together. This is relatively cool gas, so this is where stars are forming, right here, concentrated in the disk. We know that tells us that stars are forming in the disk of our galaxy. They're not forming everywhere. You start, in addition, the atomic hydrogen, which is measuring warmer hydrogen, and the molecular hydrogen together, actually, from them, we found out we have an extra spiral arm. Apparently, we lost it. I don't know. Wow. We have an extra spiral arm that we only found in gas. And in the radio wavelengths, the same wavelengths that you use to tune your car, for the radio in your car, I'm assuming some people still use radios in their cars. It turns out that there is yet another distance indicator. Our sun will stay in the main sequence. Eventually, we become a red giant. We'll become a planetary nebula, which are very pretty, and eventually die as a white dwarf. In stellar evolution terms, this is called going out with a whimper. A massive star, and by massive, I mean something 8 times the mass of our sun or even bigger, will become a red supergiant. It'll move around a bunch, and then it will undergo a supernova explosion. These are some of the most energetic events in the universe. And some of these will form a neutron star. These are the neutron stars. It was 2 neutron stars that, colliding with each other that was the recent subject of the first both LIGO and optical detection for gravity waves. And it turns out that neutron stars, in addition to being the size of being our mass of our sun, it combined in the size of Washington, D.C., spin. This is Jocelyn Bell Burnell. As a graduate student, she detected a signal. Each of these little dips is a pulse from a neutron star. What's happening is you have the neutron star here. Remember, this is the DC Beltway. Or the Baltimore Beltway, since we are in Baltimore. This is the rotation axis, so the star is spinning. This is the magnetic field. On Earth, our magnetic field lines up with our pole. In reality, in neutron stars, it doesn't. So if this is the axis, every time you sweep, you get a signal. And I'm not doing that anymore because I'm dizzy. This is a cleaner image where you can see the period, and every pulsar has a unique period. And it turns out that in addition to this, the pulses, if there's free electrons, so just electrons flying around in space, because of course there are, pulsars tend to spread out. The signal of the pulsar will spread out or disperse. If you have a pulsar where you independently know the distances, because why is this going to be straightforward, you can map the electron density of the galaxy. If you know the electron density of the galaxy and you can measure the dispersion for other pulsars, suddenly you know where all the pulsars are in the galaxy. This is the disk of the galaxy. This is 100,000 light years across. And these are the known positions of pulsars in our galaxy. So unlike the Cepheids, unlike many other things, this is one of the only tools we have to really map the far edge of the galaxy. In addition, this is something, once in a while, Star Trek actually gets something right. I don't remember whether it was Q or the Traveler that flung the Enterprise somewhere, but they're trying to figure out where they are, and they explicitly say, check the pulsars. And that is because each pulsar has a unique period. So if you identify this pulsar, and that pulsar, you now know where you are. And since I didn't know if there were going to be kids in the audience, hence the editing of the Pioneer plaque. This is not a Hubble image. This is an artist's conception, but this is based on data. This is the Milky Way. The center here with a bar. We know this based on kinematics, the velocity and the movements of the stars in the center of our galaxy. We have two major arms coming off either side. Smaller arms here, more minor arms. And then there's this additional arm here. This is the one that we figured out from radio observations of hydrogen. This is what we call the Orion spur. That's Orion. This is the Earth, roughly speaking. Not to scale, by the way. This is the furthest measurement we have in our galaxy. This is 67,000 light years away. If you remember, I told you Star Trek got the scale of the galaxy wrong accidentally. If Voyager had gone like another 10,000 light years, they would have been out of the disk. Just to give you a sense of this. That's what I mean by they got it right accidentally. This is the Earth. This is 67,000 light years away. There's about another 20,000 light years between us and the edge of the disk. And since you've been so good, I promised you that I would tell you where the Klingons were at the end of this, I believe. It turns out that the planet Vulcan is orbiting an actual star. It's called 40 Eridani. For the nearby stars, we actually have something a little more interesting than phone numbers. It is in the constellation of Eridanus, the river, which is right here. This is Orion. So if you want to actually find where Vulcan is in the sky, it's right around here. And I had to put some sort of Star Trek Discovery reference in here. This is literally what I did. In the Star Trek star charts, there is a list of about, well, actually not list, it's maps that have things written into type font that wasn't particularly easy to read. But you have a whole bunch of stars. This is for 40 Eridani, which is Vulcan in Star Trek. You have the galactic coordinates. So this is basically latitude and longitude for our galaxy. And this is the parallax. This is how much Epsilon Eridani is moving if you measure it in January and June. The larger this number is, the closer something is. And Epsilon Eridani, or Vulcan, is about 16.25 light years away. So on cosmic terms, extremely close by. In absolute terms, it would take us 17 years to say hi. And another 17 years for them to say, oh God. This is the Federation. Every single star in Star Trek star charts that was in Federation space, I plugged into the Simbad database, which is this, right there, and pulled out the galactic latitude, the galactic longitude, and the parallax, which gave me the distances. The Federation can be measured with parallax. That is how small it is. The entire Federation is about 300 light years across, depending on if you switch. I'll give them 400, because you've got some sort of weird squiggly bits that go off to the side, I think. This is if you were looking down into the plane of our galaxy. That's what it would look like. So you have sort of a tail going off here. And this is looking into the disk towards the center of our galaxy. So if Kirk is on the Enterprise on the edge of the Federation and looks back at Earth with a powerful enough telescope, he could watch Zephyr and Cochrane take off on the first warp flight. He couldn't watch us. The Federation isn't big enough for him to be able to go far enough away to look 300 years back in time. I told you I was going to nerd out. This was... Turns out the Klingons are closer than we think they are. This is the distance to all the systems, known as Klingon systems. The closest ones are actually less than 100 light years away. And if you want to look for the Klingon Empire, look in the constellations of Leo and Gemini. That's if you want to look towards the Klingon Empire. They're in Leo. It's Leo and Gemini, about 100 light years away. And I didn't know which Klingons to use, by the way, for that picture. I think this is just we got better at makeup over the course of 50 years. The Romulans, and of course I had to use green. The black here is the Romulan neutral zone. That's actually only about 30 light years away. They're actually closer than the Klingons. And the Romulan Empire is big. It goes out to about 150 light years away. If you to look towards the Romulans, you actually have to be in the southern hemisphere, in the constellation of Centaurus in the southern hemisphere. And we have the, wrong Cardassians, sorry. The Cardassians are actually if you look towards the Big Dipper. They are, if you look towards the Big Dipper tonight, you are looking in the direction of the Cardassian, what is it? Something. And these are the distances. These actually aren't distances these are distances to the edge of Cardassian space, because that's all I could find. So the answer is that, yes, this stuff is a lot closer than you think. They're not 3,000 light years away, but the chance that you could actually get across 100 light years to come and say hi, questionable. So just to put this into perspective, I told you space was big. This is the Federation, and the Klingon Empire, and the Romulans, and the Cardassians. This is all of Star Trek, with the exception of the bit that happened over here and the bit that kind of happened over here. But to give you a sense of how difficult it is to see through this mass of stuff, because remember, we're stuck in the disk. We're stuck right here on Earth looking at our galaxy through its disk. We know less about Star Trek's Delta Quadrant than we do about galaxies 1 billion light years away. It's easier for us to find out information about galaxies near the edge of the universe than it is to figure out what's going on the other side of our own galaxy. And as a closing note, the Orion Nebula is the closest major star forming to our, that was, by the way, thank you so much for mentioning Orion. That was a perfect. It's about 1,400 light years away. This is at least a 5-year mission. This is not, let's go check out the Orion Nebula and we'll be home next week. And to give you a sense of scale, remember, we're here and Orion's here. On galactic scales, this is extremely, extremely close by. As such, even in whatever future we end up in, assuming that we don't accidentally blow ourselves up in the next 10 years, astronomers are still going to be studying the universe, largely studying the universe the same way that they have been for the better part of 3,000 years, with photons, with light, physics, and hopefully really awesome space telescopes. Thank you.
All right, so if I read that correctly, if we're 1,400 light years away to the Orion Nebula, the Orion Nebula is technically not in Federation space then?
No.
Federation space is only extends for 200 light years.
It's not even close to Federation space.
It's like it's 1,200 light years beyond Federation space.
Yeah.
Okay.
And who knows who's waiting in there to
I think the Federation had better annex the Orion Nebula, okay? Because that is one of the most gorgeous places in our galaxy, okay? So I think we'll have to get it.
So then you're going to have them annex things, but you don't know who's already there.
Yeah. Well, look, I just we got to call Paramount and get their writers to get the Orion Nebula inside Federation space.
For the record, in Star Trek, if you haven't noticed, they tend to move. The Enterprise moves at the speed of plot. So it's actually very difficult to figure out how fast are they actually going and how far are they actually going.
All right. Do we have any questions for our speaker here tonight? Yes, the orange jacket.
So in this slide where the stars orbiting the black hole, so the stars are like orbiting the black hole in only a few decades because they're so close. So how fast would the stars be orbiting the black hole at the periaxis, at the closest point?
I don't know the numbers, but it is.
Can we repeat the question for the online audience?
The question is how fast are the stars are moving at periapses, that their closest approach to the black hole. I don't have a number for you. It is extremely fast. It is fast enough that when one of the ones that goes close enough approaches the black hole, they weren't sure it was going to come out the other side. So they are orbiting, basically I think it's pretty much as fast as you can go. But I don't have an actual number in meters per second.
Right. I mean, for reference, the sun is moving at what, 250, 220 kilometers per
250.
second?
250 kilometers per second. This is at least 100 times faster.
Yeah, but 200 kilometers a second times 3,600 is what, like 100,000 miles per hour or something like that, if kilometers per hour, right?
Yeah.
Just to give it something the public can
give
handle.
an order of magnitude, and these are going significantly
Things are
faster.
moving so fast in space. We talk about kilometers per second, not kilometers per hour, okay? So we always have to translate from the numbers that we memorize to the numbers we can explain. Yes, question there.
Yes, you mentioned that astrometry is one of the things that Star Trek has done correctly. I recall there were some episodes where they travel back in time, and astrometry tells them what their time that you've arrived in is. Mentioning proper motion briefly, if you want.
Okay, so the question was, in some Star Trek episodes, they travel back in time, and the astrometry of the stars tells them what time it is. Comment on that, and parallax and proper motion.
Parallax is the star moving. The star is actually moving with parallax. That's automatic. The stars are actually moving relative to the sun. Proper motions are if we're sitting here and a star is moving like this, the amount it comes across, so not along our line of sight, but across that, is its proper motion. You would assume that by the time you got to the world of Star Trek, we were actually already well into having that mapped and knowing the proper motions of the nearby stars. You would assume by the time you got to Star Trek, they would have that for a much larger volume. And so you would be able to say, Epsilon Eridani is here, but should be here, but it's here, so it must be 300 years ago.
Okay, all the way in the back in the red shirt.
I noticed on one of the slides you had the Milky Way, it was spinning. Do all galaxies that do spin, do they all spin clockwise or counterclockwise? What causes them to spin?
When galaxies rotate, do they all rotate in the same direction, or what direction do they rotate in?
It depends on what direction you're looking at them. And I'm actually not being entirely flippant. When we talk about things, it depends on what direction is up. It actually depends on what you define as up. And usually what we say is we use the right hand rule, and we say if you take your right hand like this, feel free to do this preferably without hitting your neighbor again. And if you curl your hands like this, in a counterclockwise direction, your thumb points up. So we define, if you have something rotating and you have it in the counterclockwise direction, we define this as up. And so if you were to take that same object and instead of looking at it from above, you look at it from below, you're now going to have clockwise rotation. And so the direction of the rotation is very dependent on how you're looking at
But
the
if you
object.
show the Milky Way, the picture, the Robert Hertz diagram of the Milky Way, there we go. We can say about this that they tend to rotate with the trailing spiral arms. Right. We don't know. I think I know of like one galaxy that might have leading spiral arms, which means that for this galaxy, it would be rotating clockwise. Okay. And
From the direction we're looking.
from the direction you're looking at it. Okay. Of course. Right. Just because the spiral arms trail. Okay. They're called trailing spiral arms.
So it's rotating clockwise up. So you're rotating this way. But if you were looking at the same image from the other side of the disk, it would look like it was rotating counterclockwise.
Right. We have one. We can agree on one perspective here, right? For this diagram.
We can agree on
But
one.
we can also agree that I know of like one galaxy where it was possible that it might have a leading spiral arm, but I didn't believe it actually. So it's all the spiral arms I know of are trailing. Do you know of any?
No.
Okay, good. All right, in the purple down here. So you're not in a red shirt or a blue shirt. You're in a purple shirt. So I guess you're kind of safe.
The third Star Trek thing episodes went out of the universe that we know, and they're trying to return. Where did they go?
Are you talking about Star Trek Voyager?
Voyager.
Okay, so
Hey,
where did Star Trek
Voyager.
Voyager go?
Here. I told you the 67th, I put this up for a reason. Voyager's here. They're barely still in the galaxy. Which sort of amazes me because they keep running into people every other planet. They're barely in they're up here.
Okay, over there. Yes.
The stars toward the center of the galaxy versus on the edge, are the ones more toward the center, are they traveling faster or slower than the ones?
So what are the speed of the stars in the galaxy going from the center to the edge? What's the relative speeds of those? The rotation curve of the Milky Way?
Observationally, well, the rotation curve of the Milky Way, the
Yeah.
rotation speed of the stars, is actually relatively constant with distance from the center of the galaxy. And so that means that the stars in here are actually going at about the same speed as the stars out here. This is one of the major pieces of evidence for dark matter, actually. I told you, dark matter exists. It just, doesn't exist the way that you would think it would from Star Trek. So there is, right at the center of our galaxy, as we start moving out, there is an increase in speed as you go further out. But once you get sort of out to the orbit of our sun, which is about 25,000 light years out, the speed of rotation is flattened and is constant.
Okay, in the black jacket there.
So how close does our solar system can be to the center of the galaxy before it becomes uninhabitable?
All right, so if our galaxy were closer to the center of the Milky Way, would it
Our
become
sun.
our sun? Yes. Would the solar system become uninhabitable?
I mean, I wouldn't want to be right on top of Sagittarius A. Then you might have a problem. But we could be a good ways in.
Okay.
Because remember, space is really big. We would actually have more trouble at the center of a globular cluster because of how crowded things are than we would in the center of our galaxy. So really, until you get to the really close into the galactic center, we'd be fine.
Yeah, and just to amplify her point about globular clusters are the only place that we know of where stars can actually, dense enough that stars can actually collide. So, I mean, that would cause a lot more problems than.
And to give you a sense of this, in a couple billion years, the Andromeda is going to slam into the Milky Way. When that happens, none of the stars are going to collide. That is how much space there is between the stars. The stars are actually going to just move past each other.
Yeah. But we got 4 billion years to wait for that, so.
I mean, it's like, at least you know it's coming.
That makes for a lot of sequels before that happens. All the way in the far corner.
Yes, it's really bright there in the center. Would we have an issue with light pollution?
It looks very bright in the center of the galaxy. Would we have an issue with light pollution?
I think we'd have even more issues seeing through it. I mean, right now, because we're in the disk, so the Milky Way across is about 100,000 light years. The disk is only 1,000 light years thick. You can think of it as a laser disk, is about the right dimensions. If you're in the center, if you're sort of in the bulge area here, right now, if we look up out of the disk or down out of the disk, we have a relatively clear view of what's outside the Milky Way. If we're in the middle, in the bulge, you're going to have to look this way, up, down, whichever direction you choose to look, you're going to be looking through a whole lot of stars. And so it's actually it's not so much that you're going to have light pollution as it's going to be almost impossible to see anything beyond the Milky Way.
Right. And the same is true as in a globular cluster. You get in the center of a globular cluster of 1 million stars, you can do incredible stellar astronomy, but extragalactic astronomy, really kind of difficult, okay? So yeah, we're actually kind of lucky being out in the boondocks. We have nice clear skies in one sense like that. Okay, in the blue shirt right there.
The spiral structure makes me think that the galaxy is rotating. If it's rotating, how can the outer objects be moving at the same speed as further in objects?
Okay, so if the galaxy is rotating, how can the outer objects be moving at the same speed as the inner objects?
The answer is actually dark matter.
Is what?
Dark matter. So everything we see that's visible, all the stars, the gas, the dust, starships, whatever starships, hapless bipedal species, all of that is made up of something called baryonic matter. And all of that interacts with light. It either absorbs light or emits light. All of that is about 10% of the matter in the universe. The other 90% is dark matter. And dark matter, we only see dark matter because of gravity. Because we know it's there. We know that if the stars on the outer edge of the disk are orbiting just as fast as the stars on the inner edge, then we know that the mass of the Milky Way, the mass inside those orbits, is basically the same once you get out here. So it should be falling off, like you see, like the fact that Neptune orbits slower than Jupiter, which orbits slower than Mercury. That's called Keplerian rotation. The fact that we see this flat rotation, this constant rotation, as far out as we can observe, means that there must be an additional mass component, which ends up being about 90% of the mass of the galaxy, that just isn't interacting with light. It's not absorbing light, it's not emitting light. And that is dark matter. And that's about 90% of the matter in the universe.
And I'll add one more comment that the pattern speed of the spiral structure is different from the orbital speed of the stars within it. Stars go into these spiral arms and move out of these spiral arms. So the pattern speed, the density wave of the spirals, actually is a different rotational speed than the stars that are moving through them. Okay? So that's another thing to process.
But the arms are not getting longer as time passes.
Well, we can't watch.
Getting thinner.
We can't watch a galaxy for that long to be able to confirm that. But our simulations do show that the pattern stays roughly constant for a while, but they can stretch out and reform and break up. Okay?
And for instance, when if the LMC and the SMC come too close to the disk, they will actually modify this pattern.
Okay, we got a couple questions from online.
Okay.
At warp 9.9, how long would it take for the Enterprise to cross the Milky Way?
For the love of God. 100 years. And I actually looked that up.
She did look.
I actually was ready for something like that. If they'd asked me warp 6, I would have been going,
So at maximum warp, it takes 100 years to cross the Milky Way.
It takes at a maximum warp, well, warp 9.9, depending on what maximum warp is, it's about 1,000 light years per year. Hence the reason that Orion is more than a 5-year mission.
Okay, and let's see. There was a good question. What do you think is the most interesting unanswered question you have relating to your work and your studies of things?
Well, I don't actually work on the Milky Way.
Yes.
I work on extremely tiny galaxies that are orbiting the Milky Way. And I would actually say that, going back to your first news from the universe point, I work on galaxies, very small galaxies today in the local universe, and their counterparts in the first billion years of the universe. And how that happened, how different physical mechanisms regulated and interplayed to form those first galaxies, I think is, for me, one of the most interesting problems, and we are nowhere near solving it. Webb's going to help, but we need W first as well.
Okay, and one last question from the audience. What's a laser disc?
Okay, I would say...
All right, never mind. Okay, we just got a couple more minutes. Yeah, right there.
You mentioned warp speed. What speed do you think the human race, based on physics as we know it, can go the fastest? It doesn't have to be a manned ship, but any kind of ship of any kind of satellite or any kind of device. How fast do you think possibly?
Okay, so what is the fastest we've created? Isn't that New Horizons? That's the fastest ship we've launched. And how fast do you think we possibly can go?
Do you know how fast New Horizons is going?
No. We can call Alan Stern.
Yeah, okay.
He'll have that
Or
number off the top of his
I can
head.
also call Doug Hamilton at Maryland. He probably knows this. Right now, the main way that we get things moving fast, this is true for New Horizons, which recently flew by Pluto. This is true for the Pioneer missions and for the 2 Voyager missions, is that as we go out through the solar system, we go by the giant planets. And actually, the reason we could do the Pioneer and Voyager missions when we did is because all the giant planets were lined up perfectly. right when we had the technology to do it, they just happened to be lined up perfectly, and this does not happen that often. As the planets, and so you swing by Jupiter, you get a gravity assist and you speed up. Then you swing by Saturn, Neptune, Uranus, and then Neptune on the way out. Doing that, we are nowhere near the speed of light.
New Horizons is moving at 16 kilometers a second, or 36,000 miles per hour.
So 16, to give you a sense, 16 kilometers per second is New Horizons, and the speed of light is 100,000 kilometers per second. As we approach the speed of light, because of relativity, as you start approaching the speed of light, the mass of whatever you're sending approaches infinity. So we could send something near the speed of light, or as close to the speed of light as we possibly could. But even if we got something to half the speed of light, it would take 8 years to get to Alpha Centauri. And it would take 32 years to get to 40 Eridani. So unless there's a way around this, the speed of light is the speed limit of the universe, unless there's a way around it. Of course, it's no fun you can't have Star Trek if it's like, well, we'll get there in about, 70 years. That wouldn't make for a very entertaining show.
Yeah, we scientists are a little bit dampers on Hollywood scriptwriters that come around. I've gotten a couple of scripts past me and go like, this isn't, and none of this is possible. They don't listen, but because they need it to work for their story. But we can give them our best advice. All right, here.
What's on the other side of a black hole?
What's on the other side of a black hole?
We don't know. Physics actually breaks down inside of black holes. So we understand how things work on quantum scales. We understand how quantum mechanics works, and we've been able to make quantum forces work with electromagnetic physics. But when you try to combine those with general relativity, with our understanding of gravity, the equations don't agree, and the predictions don't agree at all. And so we don't actually know what's going on inside of a black hole because our two understandings of the universe are giving us completely contradictory answers. It's actually called to unify those, to make them work inside a black hole, is one of the holy grails of theoretical physics right now.
So it's not a Snickers universe.
I mean, it could be a wormhole to the gamma quadrant, but more or less, the scientific answer is that once you're past the event horizon, we don't know.
Okay. We have an update from somebody online who looked it up, and NASA's Juno was accelerated by Jupiter, and they quote 165,000 miles per hour. That makes Juno the fastest moving human-made object in history. Okay? I didn't know that Juno had gotten up to that speed. The Juno probe that's measuring the magnetosphere of Jupiter right now was accelerated when it came past Jupiter. It's in this big, huge looping orbit around Jupiter, and somebody online says it's now the fastest human-made object in history. Okay, it's 9:24. I'll give you the honor of the last question in the back there.
And that speed is strictly gravitational, is responsible for that speed?
Well, it would have approached Jupiter with a similar tens of kilometers per second speed as it's moving out. But then because it came so deep into Jupiter's gravity well, it got an acceleration as it came through Jupiter's gravity well that increased its speed. So it's orbiting Jupiter with that speed. Okay? All right. So, understanding that Mia will be back next year, where she's going to disprove Scheinholz's theory of multiple Big
You do realize I'm
Bangs.
applying to jobs in California, right?
Yes. I'm making a Star Trek reference here, okay? Scheinholz's theory of multiple Big Bangs, which is dependent upon Wang's second postulate, okay? And so you have to get past...
Has no observables.
Yes, well, but we all know that Wang, as Captain Janeway said, Wang's second postulate has more lives than a cat. So I expect to talk about that next year. All right. But next month, we'll be staying a little closer to home. We'll be going out to Europa. We'll discover the icy plumes with Susanna de Ustua. And in the meantime, let's give a warm thank you to Mia Bovill.
Of course, that's not. I just remember all the quotes about quantum mechanics.
Yes. But there was one episode where some guy down who worked in the basement.
See, that's in the later that's in
yes,
the later
I have
seasons
no
when I
idea.
gave up watching.
Yeah, he worked down the bowels of the ship, and he was, doing a really boring job, and he was trying to disprove somebody's theory of multiple Big Bang.
By the time they got to episode season 7, he was better.